Dear audience, it's my pleasure to present this paper, Stress Corrosion Cracking Paths in Cold Drawn Pearlitic Steels, under the beautiful logo of the University of Salamanca after 800 years of history, the oldest university in Spain and one of the oldest in Europe. Two authors, Jesus Toribio and Elena Ovejero, with the Fracture and Structural Integrity Research Group of the University of Salamanca. The outline of my presentation: introduction, experimental program, experimental results, discussion, and conclusions. The introduction: the motivation is similar to the previous paper on hydrogen-assisted cracking. The manufacturing of high-strength commercial pre-stressing steel wire is made by progressive cold drawing, and this produces market orientation of the two basic microstructural levels of pearlitic colonies, ferrite cementite lamella, and it influenced the posterior stress corrosion cracking SCC behavior. The aim of the work is to analyze the influence of the cold drawing degree on the stress corrosion cracking performance of high-strength steel wires, and this represents a fracture mechanism approach to the design of pre-stressed concrete structure. There is a previous key question: is the cold drawing process beneficial from the stress corrosion cracking point of view? The cold drawing process is made to increase the classical mechanical properties, the yield strength and the ultimate tensile strength, but what about the corrosion performance? Environmental assisted cracking. The experimental program, materials were progressively cold drawn pearlitic steel wires with an eutectoid composition, 0.80% of carbon, and cold drawing produces an increase of yield strength and UTS by a strain hardening mechanism, with progressive orientation of the two levels of pearlitic colonies and ferrite cementite pearlitic lamellas. Cold drawing of pearlitic steel is shown in these two figures, two pictures of the real manufacturing process in the company, with progressive cold drawing consisting of passing of the pearlitic steel wires through several dies, an increase of yield strength and ultimate tensile strength by a strain hardening mechanism, with stress-strain curves representing in the plot stress versus strain, with a clear improvement of mechanical properties, both parameters, yield stress and ultimate tensile strength, as a consequence of the cold drawing process. You see from steel 0 in white color, not cold drawn at all, to the steel 7 that has undergone 7 steps of cold drawing. The evolution of the first microstructural level of pearlitic colonies from steel 0, 3 and 6, representing steel wires with 0, 3 and 6 drawing steps. We see in steel 0 a randomly oriented microstructure regarding pearlitic colonies, a small orientation in steel 3, and a very marked orientation after heavy drawing in steel 6, in which the colonies are markedly enlarged, slenderized, and oriented in the vertical axis, y-axis, or cold drawing direction. The pearlitic lamella also evolved with cold drawing from a randomly oriented microstructure in steel 0 to a heavily oriented, markedly oriented microstructure like a microcomposite, nanocomposite, like a laminate in steel 6, in which the lamella are almost fully oriented in the vertical direction of the right y-axis or cold drawing direction. The experimental program consisted on constant extension rate test or slow strain rate test, SSRT, on transversally pre-cracked rows immersed in aqueous environment. The specimens were pre-cracked by axial fatigue in air with a maximum stress intensity factor Kmax very moderate, 30% of K1C, to avoid plastic effects and overload retardation effects in the close vicinity of the crack tip, and two constant electrochemical potentials were used, minus 1200 millivolts versus saturated calomel electrode. That's cathodic and is associated with hydrogen-assisted cracking, and the potential regarding the analysis in this paper, minus 600 millivolts versus saturated calomel electrode, anodic potential in which the mechanism is localized anodic dissolution, there is dissolution or pure stress corrosion cracking. The experimental results are presented in the form of a plot of failure load in localized anodic dissolution or pure stress corrosion cracking, normalized device by the failure load in air, vertical axis in the left hand side. The vertical axis on the right hand side represent the time to failure under localized anodic dissolution LAT or stress corrosion cracking conditions, and the horizontal axis represents the cold drawing degree through the ratio from the diameter at any step of drawing versus the diameter at the initial stage, di divided by d0 initial diameter before cold drawing. Then we can observe a certain improvement of localized anodic dissolution resistance FLAT as a consequence of the cold drawing process. There is an increase, a clear drawing-induced increase of time to failure TLAT does exist. It implies a remarkably better localized anodic dissolution, stress corrosion cracking performance in the cold drawn pre-stressing steel wire than in the previous hot roll bar based material. With regard to fracture profile or crack paths under localized anodic dissolution LAT condition of pure stress corrosion cracking, while slightly drawn steels behave in mode 1, intermediate degree of drawing represents a certain mixed mode propagation. In mode 2, subcritical cracking, and heavily drawn steels behave in a markedly anisotropic manner with a deflection angle of 90 degrees or close to 90 degrees and a strong component of mode 2, heavily drawn steels with a propagation step. In the bottom of the slide we see the profiles with increasing deflection angle, a progressively anisotropic LAT stress corrosion cracking behavior with cold drawing. The discussion of these results with regard to the susceptibility to localized anodic dissolution, there is a surprise. We have the critical stress intensity factor in aggressive environment, K-LAT, localized anodic dissolution, divided by K1C. It is an increasing function of the cold drawing degree, the ratio of diameters. Why? There is a tremendous increase of localized anodic dissolution, stress corrosion cracking resistance of the steels with cold drawing. It may be attributed to crack blunting in the near tip area due to the anodic dissolution process itself. The blunting effect increases with cold drawing, at least in slightly drawn steels. In heavily drawn steels, the beneficial blunting effect is counterbalanced by the mixed mode propagation. With regard to the analysis of the fracture profile and the localized anodic dissolution, we have showed this picture before in 3D and in profiles 2D. We have a progressively anisotropic stress corrosion cracking behavior with cold drawing. Reason: progressive orientation of pearlitic microstructure with cold drawing at the two levels of colonies and lamella. Then we have corrosion-assisted subcritical crack growth in mode 1 that takes place over a certain distance before any crack deflection, even in the most heavily drawn steels. That's very important. There is mode 1 propagation before crack deflection in the crack path. Role of crack tip blunting in localized anodic dissolution. In slightly drawn steels, the critical stress intensity factor in stress corrosion cracking conditions, K-LAT, is remarkably higher than the fracture toughness in air, K1C. with regard to this role of crack tip blunting in slightly drawn steels, as the level of drawing increases, the progressive orientation of the pearlitic microstructure enhances crack tip blunting by selective dissolutions in directions which differ from the original propagation direction in mode 1. This ratio, the crack tip radius, is an increasing function of the level of drawing. Then the K-lab is also an increasing function of the level of drawing. Since K1C fracture toughness in air and K1SCC stress intensity threshold for stress corrosion cracking increase with the crack tip radius and thus with the level of cold drawing. The blunting effect increases with cold drawing, at least in slightly drawn steels. The aforesaid blunting effect is even more pronounced in heavily drawn steels, enhanced by the very oriented pearlitic microstructure with fevers cornered blunting over smooth blunting. Then the effective crack tip radius is higher than in slightly drawn steels. The drawing-induced microstructural orientation produces finally crack deflection, which interrupts the crack growth by localized anodic dissolution, stress corrosion cracking in mode 1, and creates a mixed mode propagation, K1 and K2, during the subcritical crack growth. Then, in heavily drawn steels, there are two competing effects. The effective crack tip radius is higher than in slightly drawn steels. It implies higher time to failure T-lat, as this plot indicates. But, on the other hand, the blunting effect is counterbalanced by the mixed mode growth. Then it means lower failure load in localized anodic dissolution F-lat. This means that there are two inverse trends of increasing time to failure but decreasing failure load. The micromechanical model could be as follows. For slightly drawn steels, there is an increasing crack tip radius with the level of cold drawing, but for heavily drawn steels, there is cornered blunting instead of round, smooth blunting. But these corners produce crack deflection by dissolution after a certain degree of cold drawing. Finally, the conclusions. 1. The stress corrosion cracking behavior of high-strength cold round pearlitic steel wires is affected by crack tip blunting created by localized anodic dissolution of the metal in the close vicinity of the crack tip area. In slightly drawn steels, both the crack tip radius and the critical stress intensity factor previous to cleavage fracture increase drastically with the degree of cold drawing, as a consequence of the blunting effect produced by dissolution. In heavily drawn steels, the blunting effect tends to increase with the degree of cold drawing, but the trend is interrupted by the crack branches created from the two microscopical kinks and the posterior crack propagation in mixed mode. And that's all. Thank you very much for your kind attention.